This video is going to talk about the standard enthalpies of formation. And what we're going to do is we're going to calculate enthalpy changes using constant standard enthalpies of formation that we can look up on a data table. So firstly, the standard enthalpy of formation, the definition is a quantity of energy associated with the formation of 1 mole of a substance from its elements in their standard states. So the key thing here is the 1 mole. Oh, shoot. Sorry, the 1 mole, and it's always from its elements in their standard state. So our symbol there has the little subscript F to indicate that it's an enthalpy of formation, and our units are still in kilojoules per mole. So the two examples I've got there are the formation of methanol from its elements. So methanol is CH3OH. So obviously the 3 elements that make up that compound are carbon, oxygen, and hydrogen. So we write out that equation with the carbon, oxygen, and hydrogen there, and then we balance it out such that I end up with 1 mole of the methanol. And then I get a standard enthalpy of formation of negative 239.1 kilojoules per mole. So same thing in the second example with aluminum oxide. I've obviously got aluminum and oxygen in there. So again, I have to make sure that I make 1 mole of the substance. So usually what we do is we write it out from its elements. So aluminum and oxygen are the elements that make up this compound. I write those on my reactant side. I balance it out. And then I have to make sure I've got 1 mole of product, because that's the whole point of the enthalpy of formation. So please make sure that you have to divide everything to make sure that your coefficient in front of your product is only a 1. So all of these elements on the left sides of the equations are in their standard states at SATP, okay? So that's straight off the periodic table. So when we write these formation equations, here are 3 steps that you can follow. Step 1, we write the 1 mole of the product in the state that has been specified. So for example, FeSO4, that's iron 2 sulfate. So if I want to write out the formation equation for iron 2 sulfate, I write that, and then step 2, I write the reactant elements in their standard states. So I have to use the periodic table for that. So the 3 elements that make up iron 2 sulfate are iron, sulfur, and oxygen. And if I look on the periodic table, I can tell that iron's a solid, sulfur is a solid, and oxygen is a gas. Notice I've also put O2 because oxygen is a diatomic molecule. Step 3, I have to balance it out and write coefficients for the reactants to give a balanced equation. And that balanced equation always has to yield 1 mole of product. So in order to do this, I put a 2 in front of my oxygen, and now I'm balanced out. So what we can do is use these enthalpies of formation to learn another way to calculate an enthalpy change, or delta H. So there's a table in your textbook that gives the standard enthalpies of formation. You will also always be given this table on a quiz or a test. So again, you won't have to memorize these. So according to Hess's law, the enthalpies of known equations can be used to calculate the enthalpy for an unknown reaction. So the example here is the formation of hydrogen and carbon monoxide gas from water and graphite is given here. Can we calculate the enthalpy change? So what we can do is we can actually use the formation equations for each of the products and reactants to create the target equation. So here's what happens. So at the top you see my target equation. Water plus carbon gives me hydrogen gas and carbon monoxide. So what I have to do is write out my formation equations for the reactants and write out the formation equations from the products. So if you look under my reactants, I have water and carbon. So to make water, I need hydrogen and oxygen. I balance it out to make 1 mole of water, and I get an enthalpy change for the formation of water of negative 241.8. That's the number I got from the back of the textbook. Carbon can't be formed. It's already in its standard state, so I can't form it from another element. So the enthalpy of formation is actually 0 because it doesn't require any energy to make it. It's already in its standard state. Now I do the same thing with the products. So if I look at carbon monoxide, obviously that's made up of carbon and oxygen. So again, I write out my equation with the elements on one side and my product on the other to get this final equation here, and I balance it out such that my product only has 1 mole. My HF, I look it up and it's negative 110.5 kilojoules per mole. And then hydrogen is in its standard state already. Okay, I can't make H2, it naturally occurs as a gas. So my enthalpy of formation of H2 is 0 because it requires no energy to make that. That's how it naturally exists. So now that I've got these sort of 4 equations, what I can do is actually add them up and then use Hess's law to find out my enthalpy change. So that's what I've done at the bottom here. So I've basically taken all of my reactants from one side of the equation and all of my products on the other side of the equation. I had to flip my first equation in order to get water on the reactant side. So you'll notice that I also flipped the enthalpy sign. Negative 241.8 became positive 241.8. And now what I can do is go through, cancel out my oxygens, and end up with my target equation. Once I do that, I now have my delta H of 131.3 kilojoules per mole. So we're combining what is new today, the standard enthalpies of formation, with Hess's law that we learned in the last video. So in general, when all enthalpies of formation are known, the enthalpy of a reaction is equal to the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants, where N is the amount in moles of each product or reactant. So if you don't want to use Hess's law, you could actually use this equation right here. So calculate the heat of combustion of methanol. So you can use Hess's law just like I just showed you and find the standard enthalpies of formation for each of the reactants in each of the products and then manipulate them and add them up according to Hess's law. The other way you can do it is to actually take this equation here and use that sum equation from the last slide. So I'm actually going to do this. And my PowerPoint's not working, so I'm just going to put this into a smart notebook file. Oh shoot, and of course, let's see if I can get this to actually work. Let's put it in black. Okay, so my question was to calculate the enthalpy of formation for this reaction. So you can do it the exact same way I just showed you, or you can use the formula that I just gave you. It's your choice. Both ways will get you the same answer. So in this case, your standard enthalpy of the reaction that's given here is going to be equal to the sum of the moles times the enthalpies of formation of your products minus the sum of all your moles times your enthalpies of formation of the reactants. So in order to do this, we're going to actually have to look up these values in that table that I told you in your textbook. So we're going to start with the products. So I'm going to do the products in green, okay? And then afterwards, I'll do the reactants in red, just to kind of color code things. So don't forget to always do products minus reactants. So in this case, I'm going to look at my products. So I've got 1 mole of CO2. So I need to find the heat of formation of CO2. And I'm going to add that to 2 times the heat of formation of water, H2O. So that is all my products. Then I'm going to subtract the same thing of my reactants. So I'm just going to write that below. So I'm going to have 1 mole of the heat of formation of methanol, CH3OH, plus, because I'm adding them up, 3/2 of the heat of formation of oxygen gas. So I grabbed these values from the back of my textbook, plug them in, and we're done. So the heat of formation of carbon dioxide in the back of your book is, so it's 1 times negative 393 kilojoules plus 2 times the heat of formation of water, which is 2 times negative 241.8 kilojoules. So we do that here. I'm just going to make square brackets there. And now we're going to subtract and plug in our numbers for our products. So I've got 1 times the heat of formation of methanol, which is negative 239.1 kilojoules. And then my heat of formation of oxygen is 0 because oxygen is already in its standard state. I don't need any energy to form that. So basically punch these numbers into your calculator, and at the very end, please actually take some time and do this. You should end up with negative 638 kilojoules for every mole of ethanol, or sorry, methanol that's burned. So again, you can write out all your formation equations for each one of these products and reactants and use Hess's law. Or you can use what I just showed you on this slide, which is using, it's the same concept of Hess's law, and you're just using a formula instead. All right, if I go back now to the slides. The last thing we've got to look at is the multi-step energy calculations. I'm actually going to do this in class one day. So several energy calculations may be required to solve the multi-step problems. You might need to use Q equals MC delta T if you've got any calorimetry type questions. You might have to use an enthalpy change. So this is where you might have a standard enthalpy that you look up, and you actually have to apply it to whatever the enthalpy change is for that reaction. You might use Hess's law, like you've learned in other videos, or you might use the Hess's law or the enthalpies of formation like I just showed you. So you might have to use those in different orders, and basically I'm going to show you in class how to do this problem. Have a look at it now, and a really good thing for you to do would be to try and solve this on your own and then see how far you can get, knowing that you're going to have to do more than one step and more than one calculation in order to solve this. So see if you can figure it out, and I will take it up in class.